Okay, now we've learned how to find the inverse of a 2 by 2 matrix, and we've done that a couple of different ways. One was the so-called long version, where you take a matrix and you multiply it by another generic matrix, and you set that equal to the identity matrix. You can do this with a 3 by 3 matrix as well. Let's say we had something like this. I'm not going to work this one all the way through, but just so you can see the process. A, B, C, E, D, E, F, G, H, I. And you want to set that equal to the identity matrix in 3 dimensions. Then each one of these row column multiplications is going to give you an entry in one of the rows and columns. So for example, the entry for, let's see, let me get a highlighter here. The entry for row 2, column 3 is going to go into the position row 2, column 3. That needs to equal 0. So just for that one row, I'm going to have 6c plus 5f plus 4i equals 0. But then I'm going to do the same thing for row 1, column 3 and row 3, column 3 to get these other entries. And that's going to give me a system of equations of system of 3 equations in 3 variables. When I solve that system, I'll know what c, f, and I are. I need to do that for rows 1, 2, and 3 with column 1 to get me the a, d, and g variable values, and rows 1, 2, and 3 with column 2 to get me the b, e, and h variable values. So the same process that we did the long version with the 2 by 2 matrix to find its inverse, we could do that with any square matrix. The other technique we used was we took this matrix here and we put it in a different order. We said that let me get my pointer here, but these two values would be reversed. So I'm going to put a 0 here and a 2 here. 0 there and a 2 there. And then the other two values, the 1 and the 3, would stay where they were but be the opposite value from what they are in the original. Then I'm going to multiply that by 2 times 0, which is 0, minus 1 times negative 3. 1 over 0 plus 3, so 1 over 3. And that gives me 0. I'm just scaling, so I need to multiply this 1/3 by all 4 entries in my matrix. Just scaling this matrix. I get 0, 1/3 times 0, 1/3 times negative 1, 1/3 times 3, and 1/3 times 2. And that was the second way that I got this inverse matrix. There is a third way, and it does work for 2 by 2 matrices, although I gave you a shortcut instead. But now I'm going to show you the third way, and I'm going to show you first on this same 2 by 2 matrix so that we can convince ourselves that it works, that this new technique works, because we'll end up with the same matrix here. So I'm going to start with the same matrix A, but this time I'm going to create something that looks a bit like an augmented matrix. And what I'm going to augment it with is the identity matrix for dimension 2. So I have my matrix A here, and I have I sub 2 here, right? So A, I sub 2. And this is not multiplication that I'm going to be doing here. It's kind of augmentation. What I'm going to do now, though, is I'm going to perform elementary row operations so that this 4 square matrix right here, these 4 positions here, become the identity matrix. But because I'm working with an augmented matrix, I can't just perform those row operations on these 4 elements. I have to perform them on entire rows, right? So that's what I'm going to do. I think what I'll do first is I'll take row 1, I'll multiply it by 1/2 because that's going to make this entry a 1, and I'll put that into row 1. So my new matrix is 1/2 of 2, 1/2 of 1, 1/2 of 1, 1/2 of 0. And I could do the same thing. I could scale row 2 by multiplying it by negative 1/3 to get a 1 here. But instead of doing that, I'm going to copy down row 2, and I'm going to do a separate operation here. What I'm going to do is I'm going to take row 1 and multiply it by 3. When I add that to row 3, Sorry, not row 3. I don't have a row 3. Let's make that row 2. I'm going to make that my new row 2, but I'm going to get row 2, this new row 2, by taking 3 times this value and adding it to this value. So that's not going to change row 1. It's only going to change row 2. So let's do that. 3 times 1 is 3, plus negative 3 is 0. 3 times 1/2 is 3/2, plus 0 is 3/2. Same thing for the next entries. 3 times 1/2 is 3/2, plus 0. And then 3 times 0 is 3, plus 1. So now I have another new matrix here, and I'm not quite done yet. I think it's going to be easier. I could multiply this row by, what would I have to do here? Multiply this row by negative 2/3 times 1/2 and multiply it by 1/2. What I'm going to do instead is I'm going to scale this row just so that I'm working with integers. I'm going to multiply row 2 by 2 and make that my new row 2. I'm going to do that up here. So if I multiply everything in row 2 by 2, then for my new row 2, I'm going to get 0, 3, 3, 2. And my row 1 is still 1/2, 1, 1/2, 1/2, and 0. And all I've done here by doing that is to make this row integers so that it's really easy to see what I need to do next. Now I need to scale this. I'm going to multiply row 2 by 1/3 and just put that back in row 2. Now I could have done that down here. I could have said multiply this, scale this row by 2/3, and that would have made that a 1 as well. That's absolutely fine if you want to do it that way. All right, so I have no change to row 1, and row 2 is 1/3 of 0, 1/3 of 3, 1/3 of 3, and 1/3 of 2. And I'm almost done. The only thing I have left to do is change this into a 0, so I'm going to multiply row 2 by negative 1/2 and add it to row 1. Row 2 times negative 1/2 and add it to row 1, and I'm going to put that in row 1. Okay, so row 2 is not going to change this time. I made a mistake down here. This says 2/2, and it should say 2/3. So let me fix that. Okay, so that's 2/3. And I'm going to multiply everything in this row by negative 1/2 and add it to this row. So negative 1/2 times 0 plus 1, negative 1/2 times 1, negative 1/2, plus 1/2. Same thing for this entry. Negative 1/2 times 2/3 is negative 1/3. When you add that to 0, you get negative 1/3. And now that this, the first 4 entries here are a 2 by 2 identity matrix, you'll notice that the entries in this part of the 4 squares match the 4 entries in what we know to be A inverse. So another way to find an inverse matrix is to take the original matrix, augment it with a square matrix, an identity matrix appropriate to its size, and then push through row operations until you end up with an identity matrix here, and the resulting augmentation, if you will, is the inverse. So let's do that now on a 3 by 3 matrix. One of the things to observe at this point is that we now have 3 techniques for finding the inverse of a 2 by 2 matrix. We have the case where you multiply this by another matrix ABCD, set it equal to the identity matrix, perform that multiplication, it results in a system. You solve the system, you get the entries here, right? That will work on any size of matrix. As long as there is an inverse, you'll be able to find it using that technique. But it's a bit cumbersome. Then I showed you just now how to take a matrix and augment it with an identity matrix, push through the elementary row operations necessary to turn this into the identity matrix, and the resulting augmented part of the matrix is your inverse. That works on all matrices too, as long as there is an inverse. The third way, it was actually the second way, I'm kind of skipping around here, was a shortcut for 2 by 2 matrices. And that was that we could take 1 over A times D minus B times C. In other words, these two values multiplied, subtract these two values multiplied, and multiply that by a related 2 by 2 matrix, reversing those two values and negating these two values, that makes that a positive 3, that would result in A inverse as well. But the problem with this technique is it only works for 2 by 2 matrices. So if I want to do a 3 by 3 matrix, find the inverse for a 3 by 3 matrix, I can't use this technique. There is a shortcut, but we don't quite have the tools that we need yet to be able to use that shortcut. And frankly, I think the word shortcut there is something of a misnomer. There is an algorithm, but it's really very tedious. So I may show that to you once we have learned all the tools that we need to be able to do it, but it's really not very useful because it probably takes just as long, if not longer, than doing it the way I'm going to show you now. And the way I'm going to show you now is using the technique I just showed you, augmenting the square matrix, and then pushing through row operations. So here's my my matrix that I'm going to work with: 2, 0, 1, 2, 3, 6, 4, negative 2, negative 1. And my first step here is going to be, that's a negative 1, is going to be to augment this with the identity matrix. 1, 0, 0. I'm going in columns just because I find things line up better for me if I do it that way. We tend to think of matrices. We're going to write the row of a matrix first, 1, 0, 0, and then the next row. You can also do it using columns. Basically, things just line up a little bit nicer. So I'm going to take this matrix now. I'm going to push through some elementary row operations until the left-hand side, this side right here, is the identity matrix. And then once I've done that, this side will be my inverse. So let's see, what should I do first? I want to have a 1 in this position and zeros below it. So I'm going to take the opposite of this row. I'm going to multiply this row by negative 1 and add it to this row. Because if I add negative 2 to 2, I get 0. So what I'm essentially doing here is negative 1 times row 1 plus row 2, and that's going to be my new row 2. So let's do that first. That's not changing row 1. It is just using it. Negative 1 times row 1, negative 1 times 2 is negative 2. And negative 2 plus 2 is 0. Negative 1 times 0 is 0 plus 3. Negative 1 times 1 is negative 1 plus 6. Negative 1, don't forget that this is a matrix here, right? So if I do this row operation, I have to do it on the whole matrix. I'm going to keep going across the entire row here. So now I have negative 1 times 1, which is negative 1. Add that to row 2. Negative 1 times 0 plus 1. Negative 1 times 0 plus 0. And then row 3 does not change. Negative 1, 0, 0, 1, and that's my new matrix. So for the next thing, I want a 0 here as well. I'm going to take negative 2 times this row and add it to row 3. So the operation I'm doing here is take row 1, multiply it by negative 2, add it to row 3, put the result in row 3. So I'll have a new row 3. I'll have no change to row 1, no change to the current row 3, and row 2. And row 3 will be negative 2 times 2 is negative 4, plus 4 is 0. Negative 2 times 0 plus negative 2. Negative 2 times 1, that's negative 2, plus negative 1, that's negative 3. Keep going though. Negative 2 times 1 plus 0. Negative 2 times 0 plus 0. Negative 2 times 0 plus 1. So now I have a new matrix, another new matrix. And ultimately, I'm trying to produce the identity matrix here. So I want 1s on these diagonals and 0s everywhere else. In other words, what I'm really trying to do is reduce this matrix. So the process that we use there is to find a pivot, make everything below it 0, find the next pivot, make everything below it 0. So I need to make this entry 0 next. And the way that I'm going to do that is I'm going to find some number, I'm going to call it a number that I can multiply by row 2, so that when I add that number to the same position in row 3, I get 0, right? Some number times this plus this puts a 0 in this position. And I want a 0 in that position. So I'm going to solve this little equation here for A. I'm going to start by subtracting R3 from both sides, and then dividing both sides by R2. And you can see that the number I need to use as my scalar is the opposite of the number in row 3 divided by the number in row 2. And it's just that position. It's just in column 2 that I'm interested in this. Now, oftentimes you can take a look at this and you can say, well, when I add whatever I multiply here, when I add that to negative 2, I need to get 0. So I need to find a number to multiply this that will turn this number into 2, right? And the only way to do that is to multiply by 2 and divide by 3. So we're going to multiply by 2, the opposite of 2, and divide by 3, the number in row 2. All right, so in this case, that number turns out to be negative, row 3, negative 2/3. Actually, it turns out to be positive 2/3 because of this negative right here. All right, so I'm going to take, let's just do it with an eraser here. I'm going to take this operation and make A 2/3. Now that I know what that number is, I can erase this work here. I also know that this software is not going to let me move things the way I'd like to, so I'm going to copy this. Oops. Actually, that is what I want. I want to turn that into, or put that in the position of row 3. I used this equation to find what my A value was, but now that I have it, what I need is to say I'm going to do these things and put the results into row 3. So when I do that, I get no change to row 1. And then I'm going to take, actually no change to row 2 either. Let's go ahead and put that in this position. And I'm going to take everything in each entry in row 2, multiply it by 2/3, and add it to row 3. Well, in the first position, you don't get anything. 0 times anything. 0 plus 0 is 0. Let's put these marks in. 2/3 times 3 is 2, right? 2/3 times 3 is 2. And that's why we did that. So 2/3 times 3 is 2. When you add that to negative 2, you get 0. 2/3 times 5 is 10/3. We do that scratch work here. 2/3 times 5 is 10/3. I want to add that to negative 3. I need a common denominator of 3. So I get 10/3 minus 9/3, which is 1/3. And so that is what goes here. Sometimes you have to do arithmetic like this, and you're welcome to use a calculator to do that. I'm not suggesting that you have to do all of it by hand, but I would strongly recommend that you leave your entries in fractional form rather than turning them into decimals. Okay, let's get rid of this scratch work because I have a couple of more entries to do, having done the work that I need to with this part of the matrix. I need to continue and do it with this part of the matrix. So I'm going to keep going, and I'm going to multiply 2/3 times this entry and add it to this one, and so on. So I get 2/3 times negative 1, that's negative 2/3. And I need to add that to negative 2. Well, I need a common denominator of 3. So I get negative 2/3 minus 6/3 is negative 8/3. So that goes here. Then I have 1 times 2/3, or 2/3 times 1. That's 2/3 plus 0. So that's just 2/3 plus 0. And then 2/3 times 0 plus 1. All right, now I have my matrix in what we call upper triangular form. We have a diagonal with numbers on it. Everything above the numbers is everything above the pivots, everything above the diagonal is not everything is a non-zero, but they can be. But everything below the diagonal is a zero entry. So we call that upper triangular form. And basically what it means is we found our pivots and now we can go about reducing it. Now, I might have been able to do this in one step, but it's going to take me two. This last row here I can see very easily. This becomes a 1 if I just multiply through by 3. So I'm going to take row 3, multiply it by 3, put that into my row 3 position. Row 1 does not change. Row 2 does not change. But row 3 is now going to be 3 times the size it was. So 1, -8, 2, and 3. All right, I'm out of room. So I think what I'm going to do is erase, I'll leave the original matrix here. I'm going to erase the scratch work. I might even leave this one here. But I'm going to erase this, this work here and much of this work here and move this matrix over so that I have a little bit more room to continue. Okay, here I am in upper triangular form. This entry is a 1, but I also need this entry and this entry to be a 1. So I'm going to divide this row by 3 and I'm going to divide this row by 2. But remember that we don't have division as an elementary row operation. So I need to write that as row 2. Let's do it row 1 first. Row 1 times 1/2 plus, no, not plus. I'm not adding it to anything, we're just scaling it. We're going to take half of row 1 and put it in row 1. And we're going to take 1/3 of row 2 and put it into row 2. As long as you're only scaling, I'll allow you to do 2 operations at once. If you're doing 2 operations that look like, I'm just going to make one up here. Let's say you had 3 times row 2 plus row 3 in row 3. And then another step was going to be 1/2 of row 1 plus row 2 into row 2. I don't want to see that as a single step from one matrix to the next. I would expect to see these 2 operations require you to write at least 2 new matrices. One for this jump here and another one for this jump here. Otherwise it gets too hard to follow. Not only for me, but also for you. If you find you need to go back and make some corrections, then it's easier to do that if you've done one matrix for each operation, each step, each elementary row operation. Okay. If you're just scaling the way I have here, then it's okay to combine them, and that's what I'm going to do in this next step. So both my row 1 and my row 2 are going to change. Row 1, I'm going to go up here, is going to be half the size it was. And that's all of row 1. So I'm going to have half of 2, half of 0, half of 1, half of 1, half of 0, half of 0. Okay, and then row 2, I'm going to cut in thirds. A third of 0, a third of 3, a third of 5, a third of -1, a third of +1, and a third of 0. And row 3 doesn't change, and row 3 doesn't need to change anymore after this because we have a 1 in the pivot, we have zeros to the left of it, so we don't need to make any more changes to row 3. -8, 2, and 3. All right, so now I have 1s on my diagonals, and I have zeros both above and below my diagonals in these 2 columns. But in this column here, I have 2 non-zero numbers above a pivot. So I'm going to need to use this row twice, once to put a 0 here, and then another time to put a 0 here. So the first thing I'm going to do is take row 3, multiply it by -5/3, add it to row 2, and put that into row 2. And then the second thing I'm going to do is take the same row 3, multiply it by -1/2, add that to row 1, and put that into row 1. But I'm going to do it as 2 separate processes, right? 2 separate steps. So for my first one, I'm going to have -5/3 times 1 plus 5/3, that's 0. My new matrix will look like this. Row 1 will not change. And row 3 will not change. Row 2 will be made up of new entries, and I'll get those entries by taking the entries in row 3, multiplying each one of them by negative 5/3 and adding it to the current entry in row 2. So the first one is negative 5/3 times 0, 0, plus 0 is 0. Negative 5/3 times 0, I'm in my second entry here. Negative 5/3 times 0 is 0, plus 1 is 1. Negative 5/3 times 5, sorry, negative 5/3 times 1 is negative 5/3, plus 5/3 is 0. And that's it for the left-hand side here, but I need to keep going. I need these entries as well. So I have negative 5/3, I'm going to write this one down, negative 5/3 times negative 8 plus negative 1/3. So I'm going to get here, this is over 1, I'm going to get 40/3 minus 1/3, that's 39/3, which is 13. So that's what goes here. It's just a little bit of arithmetic. Feel free to do this on your calculator. I don't have any issue with that. If you do, you can use, if you're using a TI-84 or 83 specifically, you can type the math key and then enter twice, and it will turn whatever display, whatever decimal display you have on the screen into a fraction. Better still, it puts it into the reduced fraction. So you won't get 39/3, you'll just get 13. Math, enter, enter. In case you don't know, already know that trick. So that's my first 4 entries. My next entry is negative 5/3 times 2. Let's go up here. Negative 5/3 times 2 plus 1/3. Negative 5/3 times 2 plus 1/3 is negative 10/3 plus 1/3. That's negative 9/3, which is negative 3. And my last entry here is negative 5/3 times 3 plus 0. Those cancel and I get just negative 5. Okay, so that is row 2, and I now have the pivot and zeros either side of it. So the last thing to do is get rid of this one here, and I've already identified the operation that I want to do that will get rid of that, so let's go ahead and do that. In this case, row 1, where am I? Row 1 is the thing that's not that's going to change. The other 2 rows are not going to change. So there we are. The only one that's empty is row 1, because I'm now going to take negative 1/2 times row 3 in this matrix, negative 1/2 times each entry in row 3, and add it to row 1. Negative 1/2 times 0 plus 0 gives me 1. Sorry, negative 1/2 times 0 plus 1. Negative 1/2 times 0 plus 0 gives me 0. Negative 1/2 times 1 is negative 1/2. Plus 1/2 is 0. Negative 1/2 times negative 8 is positive 4. Positive 4 plus 1/2 is 4.5, which is 9/2. And I have negative 1/2 times 2, which is 1 plus 0. And negative 1/2 times 3, which is negative 3/2 plus 0. And I've just noticed I made a mistake in this entry here. I should have had negative 1/2 times 2 is negative 1 plus 0, so that should be a negative. All right, so now this part of the matrix is an identity matrix, right? It's a 3 by 3 identity matrix, which means that this part of the matrix is A inverse. This part right here is A inverse. And I would invite you to try taking matrix A up here, right here, this matrix here. Try taking A and multiplying it by A inverse, and try taking A inverse and multiplying it by A. In both cases, you should get the identity matrix in dimension 3. Now, I want to apologize that this video is so long, but there's one last thing I want to tell you about finding the inverse of an n by n matrix using this technique. We were finding the inverse of a 3 by 3 matrix. It is also a 3 by 3 matrix. I'm going to erase the screen because I want to kind of give you an example of something that might come up. If as you are working through this process and you get down to the place where you have your identity matrix on one side and you're just finalizing the last elementary row operation, and you end up with a row, it doesn't have to be row 3, but any row that's all zeros, then there's a problem. Just as when we were simply reducing matrices and we got to a place where we had all zeros, there was that basically what that means is there's no solution, right? So because the problem that we're actually trying to solve right now is find the inverse matrix, this tells me that A inverse does not exist for whatever does not exist for whatever A was. It doesn't have an inverse. There are square matrices out there that do not have inverses. So this is a possibility. And it's just something to keep an eye out. If this happens, and as I said a minute ago, it doesn't have to be row 3. It can be row 1 or row 2. It can be any row in your right-hand side matrix. If you get to the point where you have an identity matrix on one side, but you have a row of zeros on the other, then you don't have an inverse. There is no inverse for that matrix.